Hi, my name is Lauren James, and I'm presenting my research that is a part of my Applied Meteorology graduate program. The goal of this study was to examine whether modern hurricane-resistant residential construction actually reduces damage during major hurricanes and whether living in these homes influences evacuation behavior. Today's presentation will begin with an introduction and the motivation for the project. Then I'll discuss the scientific background and previous research before explaining my data sources and statistical methodology. Next, I'll present the results of my analysis, discuss what they mean, and acknowledge the study's limitations, and conclude with recommendations for future research. This project brings together meteorology, engineering, emergency management, and statistics to better understand residential hurricane impacts. Rather than just looking at the storm itself or only building construction, I wanted to evaluate how both the physical hazards and the characteristics of the built environment contribute to disaster outcomes. Hurricanes remain among the most expensive and destructive natural hazards in the United States. As ocean temperatures continue to warm and coastal populations continue to grow, more people and more homes are exposed to hurricane hazards. At the same time, building codes have improved significantly over the past several decades, and modern construction techniques are designed to better withstand hurricane force winds, which reduces structural damage and improves community resilience. However, an important question remains. Do these storms actually reduce damage during extreme storms? And could living in a hurricane-resistant home influence how residents respond to evacuation orders? Understanding these relationships can help improve mitigation strategies, emergency planning, and public safety messaging. The primary research question for this study was, does hurricane-resistant residential construction reduce residential damage intensity and improve disaster outcomes, specifically during Hurricane Ian? To answer this question, I established three hypotheses. The first hypothesis proposed that counties with a higher percentage of hurricane-resistant housing would experience less residential damage. The second hypothesis proposed that stronger hurricane hazards, especially wind speed and storm surge, would result in greater damage. The third hypothesis proposed that stronger storms would correspond with broader evacuation orders. To evaluate these hypotheses, I analyzed data from 26 counties in Florida that were impacted by Hurricane Ian directly. This next section provides the scientific context for this project. Starting with the background of Hurricane Ian, which made landfall in southwest Florida in September 2022 as a Category 4 hurricane. This storm produced destructive winds, significant storm surge, heavy rainfall, and widespread flooding across much of the state. Ian became one of the costliest hurricanes in Florida's history. Because different counties experienced different levels of wind, surge, rainfall, and damage, Ian provides the perfect case study for comparing how varying hazard intensities affect residential impacts. Previous research from several disciplines guided this study. Engineering research has consistently shown that stronger building codes reduce structural damage caused by hurricane winds. Meteorological research has identified that wind speed and storm surge is the primary physical driver of hurricane damage. Emergency management research, particularly the Protective Action Decision Model, explains that evacuation decisions not only depend on hazard intensity, but also on how individuals perceive their personal risk. While each of these topics have been studied independently, relatively few studies combine engineering, meteorology, emergency management, and FEMA recovery data into a single statistical analysis. That research gap motivated this project. I will now discuss the data that was used in this analysis. This study includes 26 Florida counties that received FEMA individual assistance declarations following Hurricane Ian. These counties represent the areas experiencing the greatest residential impacts from the storm and include both coastal and inland communities. Using counties rather than individual homes allowed multiple public data sets be integrated into one comprehensive database. The dataset combines information from several authoritative sources. FEMA provided residential damage and disaster assistance information. NOAA, the National Weather Service, and the National Hurricane Center provided meteorological variables including wind speed, storm surge, rainfall, and the distance from landfall. The U.S. Census Bureau supplied housing and socioeconomic characteristics. And finally, county emergency management offices and the Florida Division of Emergency Management provided evacuation order information. Combining these sources produced a county-level data set containing 26 observations. The variables were grouped into 4 general categories. Meteorological variables included wind speed, storm surge, rainfall, and the distance from landfall. Residential characteristics included the resistant housing percentage, median home age, and median home value. Impact variables included residential damage intensity and the FEMA disbursements. Finally, the emergency management variables included evacuation intensity scores. And please see the image below to see how I derived the 0 to 4 intensity level scores. This was a quantitative observational study. After collecting and cleaning the data, I calculated several derived variables, including the actual damage intensity and resistant housing percentage. Because the damage variable was highly skewed, I applied a logarithmic transformation to satisfy the assumptions of linear regression better. The statistical analyses included descriptive statistics, correlation analysis, multiple linear regressions, coefficient plots, and model diagnostics. All of these analyses were performed with R. After integrating all the data sets, I created derived variables that were needed for the analysis, and then I performed descriptive statistics to summarize the data and generate visualizations to examine the distributions and relationships. Then I calculated Spearman correlations, and then finally developed the regression models to determine which variables best explain the residential damage. The diagnostic tests confirmed that the final model met the assumptions reasonably well. So now let's present the results. I first examined the descriptive statistics by taking a look at the measures of central tendency, the percentiles, and the distribution moments to better understand the characteristics of each variable before developing the regression models. The meteorological variables show substantial variation across the study area. The mean and the median, which are the measures of central tendency, show that the average wind speed across the counties was about 75 miles per hour. Looking at the percentiles and the minimum and maximum values shows the wide range of the hurricane conditions experienced across Florida. Lee County, where Ian made landfall, experienced the highest winds of 150 miles per hour and the highest surge at 15 feet. In contrast, Charlotte County received the greatest rainfall at nearly 27 inches, while St. Johns County, which was more than 230 miles from landfall, can demonstrate how the Ian's impacts extended far inland. You also may notice that a few counties have negative storm surge values, and those are not errors. They represent a phenomenon called the blowout tide. So as hurricane was making its way before landfall, some strong offshore winds pushed water away from parts of Florida's Gulf Coast shoreline and caused water levels to drop below their normal tidal level. So counties closer to landfall experienced the strong onshore winds, and that produced that catastrophic positive storm surge that we're more familiar with. Rainfall also varied considerably among the counties, and the differences between these counties shows that Hurricane Ian had varying hazard intensities depending on where you were in Florida. The residential variables also showed considerable variation. On average, approximately 31% of homes were classified as hurricane resistant. St. John's had the highest percentage of hurricane resistant housing at approximately 53%, while Pinellas County had the lowest at about 11%. Actual residential damage intensity averaged at about 2%, although some counties experienced substantially greater losses. Interestingly, the greatest residential damage occurred in DeSoto County rather than Lee County, which demonstrates that hurricane damage depends on more than just one hazard variable. FEMA disbursements varied dramatically, reflecting the uneven impacts of the storm across Florida. I also examined the third and fourth moments, specifically the skewness and the kurtosis, to evaluate whether these variables followed an approximately normal distributed shape. Several variables, particularly the damage intensity and the FEMA disbursements, were highly right skewed because only few counties experienced extremely large impacts. Because of that positive skewness, it justified me using the log transformation for the damage variable before performing the regression analysis. So we see that Lee County had the strongest winds, the highest storm surge, and received by far the largest FEMA payout, nearly $488 million, but DeSoto had the highest damage intensity at around over 12%. This is because damage intensity is a normalized measure rather than a measure of total losses. Lee County had a much greater total damage and FEMA assistance because it has a larger population and housing stock, whereas DeSoto County has a higher proportion of residential damage relative to its housing. Median home age across the counties was approximately the year 1989, while the median home values roughly averaged around $275,000. Median home values range from $91,000 in Glades County to nearly $700,000 in Monroe County, which illustrates the socioeconomic diversity across the study area. Vehicle dependency and evacuation scores also varied across the counties, providing additional variables for examining evacuation behavior. These visualizations illustrate the distributions and relationships observed in the data and supports the statistical analyses that are presented next. This slide presents the most important findings of the study. This is the final regression model, and it explains approximately 60% of the variation in the county level residential damage. Among all the predictor variables, wind speed was the only statistically significant predictor with a p-value of 0.038. Rainfall showed a marginal relationship with damage, but it did not reach the statistical significance, which is the 95% confidence. Storm surge, resistant housing percentage, median home age, and median home value were not statistically significant after controlling for the other variables. These findings indicate that at the county scale, hurricane intensity, particularly wind speed, is the dominant driver of residential damage. This coefficient plot summarizes the regression results visually. The variables whose confidence intervals cross the zero are not statistically significant. Notice that wind speeds stand out as the strongest predictor, while the confidence variables for the remaining variables overlap zero. This provides a visual confirmation of the regression results. I'll now return to the original hypotheses. The first hypothesis, that greater hurricane-resistant housing would reduce damage, was not supported statistically. The second hypothesis was partially supported because wind speeds significantly increased residential damage, while rainfall showed a marginal relationship and storm surge was not statistically significant in the final model. The third hypothesis received weak support because evacuation intensity increased descriptively with hazard severity, but the evacuation model itself was not statistically significant. Overall, these findings suggest that during an extreme event like Hurricane Ian, storm intensity appears to outweigh the county-level housing characteristics when exploring residential damage. The most important takeaway from this study is that wind speed remained the strongest predictor of residential damage, even after accounting for housing characteristics and socioeconomic variables. This does not necessarily mean that hurricane-resistant construction is ineffective. Instead, it suggests that county-level averages may be too coarse for detection of the protective effects that occur at the neighborhood or individual home scale. It is also possible that Hurricane Ian was just too intense simply to see the differences in housing characteristics, so it became more difficult to detect statistically. There are several important limitations to acknowledge. First, the sample size included only 26 counties, which limits statistical power. Second, county averages can mask important neighborhood level differences. Third, several potentially important variables such as elevation, construction quality, and actual evacuation compliance were unavailable. Finally, Hurricane Ian was an unusually severe event, and results may differ for less extreme hurricanes. Future research should expand this work in several ways. Using parcel level or individual home datasets would allow researchers to better isolate the effects of building age and construction quality. Analyzing multiple hurricane seasons or multiple states would substantially increase the sample size and improve statistical power. Future studies could also incorporate resident surveys to better understand evacuation decision-making and the perceptions of hurricane-resistant construction. In conclusion, this study found that wind speed was the strongest predictor of residential damage during Hurricane Ian. Contrary to the original hypothesis, county-level hurricane-resistant housing percentages were not statistically significant after accounting for these storm characteristics. These findings suggest that the physical intensity of the hurricane remained the dominant driver of damage during this extreme event. However, the absence of statistical significance should not be interpreted as evidence that stronger building codes are ineffective. Rather, this highlights the need for higher resolution data to better measure the localized resilience. Overall, this study contributes to our understanding of how engineering, meteorology, emergency management all intersect during these major hurricanes and provides a foundation for future research. Thank you for your time and attention, and I'll be happy to answer any questions. I've also provided my references, and there's an appendix.